Okay. All right. Hello, everyone. So a couple announcements before we start with the actual lecture. First of all, the homework assignment is up, but there also were a few errors. Some people were pointing them out on the message board, and those are being fixed as we go. This is sort of the life when you have a class being taught, at least by these instructors for the first time. There might be some typos in the assignments. They're pretty minor so far, so if you find something you think is a typo, just let us know. We'll try to correct it as fast as possible. The other thing is the homework should be all out, but the auto lab system is still sort of undergoing some churning in the background. You should have all gotten an email saying you were added to the system. Is that right? They should have gotten an email.
I think so.
Okay. Okay. So check if you can access AutoLab, as in log into AutoLab under your Andrew ID. You can't submit anything yet. I think by the end of today, we'll have at least, we'll kind of just divide them up. So they're having some problem with CVX-Pi, as you can imagine, getting those on the VMs there. So it will be all set up. There won't be an issue, but please check today to make sure you can do it. And the other problem should be up just shortly, right? The other assignment. We'll break them into two parts. Secondly, who all, by a show of hands, has installed CVX-Pi on their system? Okay, so about maybe a third. We're lucky. So please try to do that soon. This is something that you will, as you've seen from the Piazza posts, there are some issues with this. Apparently some people are having trouble. The auto downloads that go along with these things aren't working for some people. I'm not quite sure why, because they have worked for me, but we'll try to debug that. I guess, Vittoria, you're going to have office hours tomorrow, and although they're just general office hours, they'll sort of also be reserved a little bit for people that are wanting to help setting up CVX-Pi on their own system. So we have instructions now for Mac, Ubuntu, and PC and Windows, but doesn't cover all our bases. It hopefully covers enough of our bases. But let us know if you have problems with that, because that is going to be a key part of this assignment and also of future assignments as well. Is there anything else we need to add? I guess you don't know about it yet, but there also might be a change of schedule. But we'll talk about that afterwards. We might have a lecture on mixed integer programming next time as opposed to planning. But that's news for you as well. So, all right. Well, I think, are there any questions sort of on administrative things? Not on the content, because we'll get to that shortly, but on the homework or on the general sort of setup of the problems. Okay, well, we have office hours too, so.
Okay, so today we're going to talk about constraint satisfaction problems, and we'll define what constraint satisfaction problems are, and we'll talk a little bit about how our familiarity now with search helps us solve constraint satisfaction problems. All right, I'm going to try this thing. We'll see if my technology works. Great, it does. Wonderful. So here what we have is a constraint satisfaction problem. Is the first idea of this is to sort of deconstruct the problem that you want to do into a set of variables. And then you think about assigning values to those variables, and that is basically the solution to a problem. All right, so formally we have what is a constraint satisfaction problem is a set of variables, x1 through to xn, and a set of constraints, and we'll talk a little bit more about what constraints look like. But think of them as ways of restricting the values that certain variables can be assigned. Okay, and a solution to a CSP or constraint satisfaction problem is a complete assignment to all variables that satisfies all the constraints. All right. The representation of the constraints is usually as predicates, meaning that if such and such holds, it's either going to be true or false, and if it's false, then that constraint is violated. All right, and you can kind of visualize CSP as a constraint graph, and we'll talk about what a constraint graph looks like. So one of the, if not the most popular and prototypical constraint satisfaction problem is called a map coloring problem. And often you'll see the country of Australia for it. And a simple problem here would be, how do you color each of the states and territories given a restricted set of colors, say 3 colors, red, blue, and green, such that no adjacent state or territory has the same color? Okay? And so if you think about it, these are the nodes. Each node represents a variable, and you'll be assigning to that node a color, and that would be the value to that variable. And that's what you're trying to solve here. And the constraints, basically, if you look at all the constraints here on these edges, they all say that they cannot be of the same color. Can't have the same value, any of the adjacent ones. Okay, so that's an example. That's an example of what's called a finite domain, and that means that there are a finite set of values that you can assign to the variables for the solution. In this lecture, we'll be focusing on the finite set of ones. It's more difficult, and there are more specialized means for doing the infinite domains where you can, or at least continuous domains where you have many values that you can assign to the variables. So some examples of the finite ones are the 8 queens problem. And for the 8 queens problems, you can imagine each column being a variable, and then the value would be the assignment of the queen in one of the rows of that column. So if you had 8 across, you have those 8 variables, and then you just assigned the row would be the values that you'd be assigning to it. And the kind of constraints you might see are things like saying that no 2 queens can be able to take each other. Infinite, there's also these kind of matching cryptomath. I'll give you an example of this cryptomatic problems and sort of job assignments. You have a bunch of jobs, and you have people that have to do it, and you're trying to assign those resources to those jobs. The infinite domains or continuous domains, basically the number of values that you can assign to the variables are much too large, and you can't really assign them, so you have to figure out better ways to do it. There are special ways to handle particular classes of those kinds of problems. Often you need something like a constraint language. The holy grail in constraint satisfaction problems is to come up with this ever completely comprehensive expressive constraint language that could represent all the different ways, and then you make this generalized constraint satisfaction problem solver that can take in all those omni constraints from those constraint satisfaction problems and spew out an answer. That has always been the holy grail. It has remained a grail and nothing more. It's unapproachable really at the moment. So some of the things that you might see as a kind of language is this kind of language for constraints. This would be for a scheduling problem, and you can imagine this would say the start of job 3 has to start greater than sort of the start of job 1 plus 5. And that would be something where you're having staggered starts basically. And you can imagine even an upper bound on this start job, saying that it has to start between 5 minutes later than I started job 1, and maybe no later than 10 minutes. Something like that. Where actually later on in this course we'll go through some scheduling approaches for how to do scheduling. That's a luxury I get to do because that's my area, so I get to give you a little bit more specialization on that. But today we're not going to go through that. All right, so here are some of the general steps for solving CSPs using search. As I said, we're going to use search to assign those values to the variables. The initial state, as you might imagine, is you have a bunch of variables and they have no values assigned to them. All right, and then the second thing is you have the successor function, and that's that a value can be assigned to any variable as long as no constraint is violated. So you can go ahead and assign a value to a variable and then check all the constraints to make sure you're not violating anything. And keep doing that. The goal test is going to be you have an assignment that has values to all the variables and you have no conflicts, no constraint violations. And the path cost, which isn't so important here, is it's going to be a constant cost for every step. If you're trying to figure out better, quicker solutions, then that path cost comes into account. But remember, the solution that you're looking for is this sort of an assignment of values to variables that don't violate any constraints. And you don't, to a certain extent, you don't care how you got there. And we'll see how that shows up. So here's one of those problems we've seen before. This idea is how do you assign values to each of the letters here such that this all makes sense. And I'm not going to go through this example, but I mean too much. But for example, here we're trying to figure out, all right, how do we want to formulate this into a constraint satisfaction problem? So one way we wanted to do this is we're going to make sort of this graph, and we say, well, we know that these should all be different. So that might be that. Imagine that's what that stands for. That constraint up there. This one says all these should be different. These are introduced variables that you add, because you realize that if you're doing adding, you're going to have carryover, right? If you go above 10 or above the magnitude. So these are these really represent the carryover variables. And so you can imagine here, like 0, the O plus O is going to equal R, plus if there's any carryover. So that's what the X1 shows here. And again, you do the same thing for each one of these things. And this is just showing that they're and x3 equals f, because you know that up there. And you know, because you don't have any carryover until there. So these all represent ways of constraints of which you're going to be able to assign the numeric values to those pieces. So it's just a layout of how the problem looks. OK, so before I go too far, I keep saying constraint satisfaction problems. And satisfaction is the key point here. Satisfaction means any assignment that will solve, that you can assign to all those things and have no constraint violations. It doesn't say you're trying to optimize something. It doesn't say you're trying to do better at something. So you can imagine trying to do a resource allocation problem where you're trying to do optimal allocation in order to be able to satisfy a bunch of requests that's going to use those resources. If one thing you would need to know is what does optimal mean here. Optimal might mean use the resources as little as possible. All right. Or some kind of cost that you want to minimize, for example. So that would be something you would do in constraint optimization. You'll see the COP. That's a different problem. It's similar, but it's much harder. It's a much harder problem. It's often hard to find optimal solutions. There's only any kind of real-world problem. You aren't going to find those very often. So in those optimization problems, we'll have a different way of looking at them. We'll have these kind of metrics, as I say, that you're trying to optimize, some objective function. We're not going to focus on that in this lecture here, but I'm just making you aware of the difference between COP and CSP. One other distinction often is something whether you're doing it in a centralized manner or you're doing it in a distributed manner. So you'll see something called distributed constraint optimization problems. Those are things where there's no centralized view of where you know what all the variables are going to look like. You have partial views, and people are sharing information back and forth in order to get the kind of state where they can actually do the check for violations of the constraints. All those kinds of things, which you can imagine is made very easy in the centralized world, but it's very hard when you only have partial observability of those other agents. So those kind of things, those distributed COP problems, you'll see in multi-agent systems typically, and those kind of papers. One other thing you'll see is something called dynamic constraint optimization problems, and that's typically when constraints can change as the problem is executing. Okay, and that gets to be a little bit more complicated, even, as you can imagine. But again, just setting the context for this, we're going to be focusing on sort of mainstream constraint satisfaction problems right now. All right, so sort of a naive application search to CSPs. I mean, one way that you could imagine just naively brute force doing a search to assign those variables, those values to those variables, would be to just start the search and say, all right, I'm going to start giving a value to this variable, this variable, this variable, this variable, each one on the apply in the first search, and then go pick another variable and give a value. So if you have a variable A, you might say that's 5. Then the next apply down for that would be B, C, and D if those were the different variables that you're assigning. And then on that first apply, you might start, the next one might be B with some value that's in the domain that's legal for B, and then you're going to go down and assign the next one in the search. So you can imagine having, basically looking at assigning all the variables some value at the top tier of the search, and then keep reducing the number of variables you've done and assigning values that are legal based on there's no violations. But there's a couple reasons why you wouldn't do it that way. One major reason. First of all, if you look at that, the branching factor is very big. If there's n variables with a domain of d values, possible, just imagine that for each of those variables, then at the top level, there's going to be n times d at the top level of nodes, and then it's going to n minus 1d as you go down, and so on for n levels. So what you end up having is you end up having a tree that could potentially have n factorial times d over the n leaves, which is obviously way, way, way huge. It's not going to be tractable in any kind of computational search. So what's one of the things that's wrong with this thought? Well, as I said, remember I said earlier in the lecture, I said that there is no, you don't really care how you got there to a certain extent. All you care is that you have an assignment. So all you need is a value per variable. So it doesn't matter about the order in which you do those into the extent of getting to the solution. So they're commutative in that sense. So don't do it that way, right? The better way is just consider a single variable at each depth of the tree. Because it doesn't matter if you do it at the top, as long as you get those assignments. So, because eventually you're going to have to assign some value to every variable. So for an example here now is, so remember back to our map coloring problem. Here we have the WA variable, and we're trying to assign a color to that WA Western Australia variable. And we just do it at this top. We don't look at all the different ones. We just pick this variable, pick one of the variables and assign a value to it. Because we don't care about the order that we do it in. At least not in the solution, but we'll find out about how the computation will. We do care about the order. Then we say here, oh, okay, we're going to pick the next variable, which is NT here, right? Northern Territories. And then we assign colors here, and assign down here. And then now we can see we've reduced some of the complexity of the tree by a lot. Nevertheless, it's, in any kind of real-world problem, it'll become vastly huge. Okay, but still, this is the typical way you formulate it, is that you look at it this way, one variable at a time. It doesn't really matter the order that you do it in. Except, and now we'll get to that too. So the kind of a simple backtracking algorithm, this should look very much like, what would you expect this to look like? Something like, what search did we looked at before? Kind of a depth first search maybe, might work fine here, because you're limited by the number of variables, so you don't have to worry about that too much. So here we come here and we have the CSP problem that's put in, and we're going to either say that we get a solution, the solution being the assignment of the values to the variables, or we got nothing, and it's failed. So here's some of the ways that we can do this. If an assignment is complete, that means that we have a consistent set of values assigned to the variables without any kind of constraint violations. Then we just return that assignment and we're done. If not, then we select an unassigned variable right here. And we'll come back to this in a moment about how to sort of improve this search technique, this one and this one. So we select a variable, and then for each of those variables, we pick a value. If the value is assigned is consistent, there are no constraint violations, then go ahead and call recursive backtracking again. So now we're going down the next tier on our depth first search. With this new value assigned to this and what's the remaining unassigned variables. And we keep going down as you go down the search. And if the result is a failure, then, if the result is not a failure, then return that result and we have to complete that assignment. If it is a failure, then you're going to kind of backtrack up the search in the recursion and try the next set of values. And that way, you basically just going down depth first, assigning variables. If any of them fail, you go back up and try the next pass. Okay. So some of the key questions are, which variables should be assigned next, and in what order should the values be tried? So one of the things, as I said, it doesn't matter how you get there. But in terms of the computation and the complexity of it, some ways are better than other ways, right? You might get there to a solution faster. And there are ways of which you don't have to backtrack as much, basically, in that simple search. So what are some of the ways that you can guide that? It says which variables should be assigned next, and in what order should the values be tried. So when you're looking back here, and you're looking for select an unassigned variable, which one you pick here might be important in terms of how fast you find a solution. And the same thing can be said for even given a variable, some values may be more constraining than other values. So it might be important to say which value you try first, because that will be tried earlier in the search. Okay. So also in a sort of greater scales, what are the implications of the current variable assignments for the other unassigned variables? Basically, given a set of variables, it's caused a bunch of constraints to be enforced, which is going to affect the possible values that can be assigned to the unassigned variables. And so you want to look at that consequence to decide what might be able to be a faster way to find your solution. When a path fails, can you avoid repeating the failure in subsequent paths? Some of the things that the people come up with is very much like the visited node list, but it's kind of what they call no goods. If you come back to that state, don't even bother trying it, don't expand it, don't even look. Okay, so here are some common heuristics that they use for deciding which variable to choose in that search and which value you might assign. So one of the variables you might use is the most constrained variable heuristics. And that means that if you have a notion of, given the assignments that you've made so far, if you can look at the domain of the variables that are remaining, the domain for each one of those variables, and say which one of them has the smallest number of available values to that variable, maybe I should try the most constrained one first. It has the fewest number of variables of values that can be assigned to that variable, so I'm going to try that variable first. All right. These are heuristics, so they're not guaranteed to do well in all domains, but it's something that allows you, typically in a lot of domains it performs well. Another one is the most constraining variable heuristic, and it says of these remaining variables that are out there, if you look at the constraints as, and you think of them as a graph, and you think of them as having edges, each one of them is a node, and you have edges which represent the constraints, which one has the most edges to it? Meaning it's involved in the most constraints. If it's involved in the most constraints, maybe that might be something limiting. So let's try that first. So that's another heuristic. Another one is the value reordering heuristic, and that says, well, maybe I should pick a value. I'm going to remember the second one is picking a value once you've chosen a variable, and we say I should pick a value that will not constrain, will constrain the other values and other variables the least. So if you have some sense of that, you might pick a value. Now the question is, how do you get that sense of who's going to restrict the least? And we're going to go through and look at some of the techniques that they do for that. Does everybody follow that so far? Okay, great. So here's something that's this kind of forward checking is a way of seeing what some of the domain values that are available after you make certain assignments doing the search. So the ideal here is that you go down here and you go ahead and you do that. Remember we said that first variable we're going to assign into red. If we remember that search we were doing here in the map coloring problem. As soon as we do that, we look at all the adjacent ed ones and we said, well, they can't be red, right? So I'm going to pluck them off the possible domains for those variables. And you can see that they get knocked off here. And then we'll do the same thing as we come down here. We'll do another assignment if it's green, and we say, okay, there's green. There's only going to be one variable available over here, a few variable values here. We come down here and we try blue on V, and sure enough, we come down here. We go assignments, and suddenly we have a variable that has no possible values, right? So if a variable has no possible values, you know that search is time to stop that branch. It's not going to work out. You have to go back. You're going to backtrack out. So it's a way of kind of, quickly only trying the branches, the values that make sense. And the second thing is to also stop the search when you no longer have possibilities or when you have a complete solution. So it's another way of pruning down the search space. A little stronger way of pruning down the search space is something that they call arc consistency. So an arc consistency, an arc from x to y in a constraint graph is consistent if for every value in x, there's at least some value of y that is consistent with x. So if you have these dependent variables and you have the constraints, you can say if there's for any value that's in x, there's going to be at least some value in y that will be consistent with that. And it won't end up with an empty domain. Y won't be. So you can detect some more consistencies in this forward checking. You can do it in kind of two different ways. You can do it a priori. You can sort of just do it up front and reduce the domains for each of the variables upset by just propagating through all the variables and all the constraints and seeing how much you can prune off. Or you can do it as you're doing the search, and then you can limit how much you want to do this R consistency just for the variables that you're looking at. And you don't have to look at all the variables. Two different ways to apply it. This process has to be applied repeatedly. Can it make sense why it has to be done repeatedly? I think when I show the search algorithm, it will make a little bit more sense. Anybody have a guess about why it would have to be done repeatedly? Well, let's look at the search algorithm, and then maybe I'll ask the question again. So there's lots of different constraint problem algorithms, but one that's been very popular for a number of years, mainly because it's both simple to implement and because it's pretty generalized, easy to use. The 3 stands for that there are 2 versions before this one, so it's AC3. Returns, basically you take a CSP and it says, and it'll return false if the inconsistency is found or true otherwise. So if you end up, when you're trying to force through all these variables and through the constraints and find out what the possible domains are after checking for all the violations, and saying, oh my god, this variable has no values that are possible to assign to it, then that would be an inconsistent state. One of the things that's talked about, and I didn't talk much about this, is that it takes a binary CSP. We talked about binaries just basically between 2 variables, constraints between 2 variables. You can imagine, tertiary or any higher order number of constraints, in which case you can reduce them. Just like anything else, you can always reduce them to pairwise comparisons. All right, by introducing new variables if you have to. So imagine, from the point of view here, is that the CSP is a binary constraints, meaning that each variable, each constraint will look like variable between 2 variables. This has to hold. Basically, this property has to hold. So local variables are a queue of the arcs. So those are the constraints initially in the CSP. The arcs represent the constraints. And you go through and it says while there are constraints that you're going through here, while they're not empty, you look at the variables x of I of x of j as the constraint goes from arc goes from x of I to x of j, and you do this remove the first one to get that, and then you check it to see you want to revise the possible values that might be assigned within it using this revise function. So given x of I, you're going to look at all the possible values in, for each x in d of I. You're going to look to see if there's any, if it's ever the case that you can't find a value in y that you can assign to y, that will be consistent with x. If you can't, if there's not one value that will work for that, then you know that you have to prune that value off the domain from x, right? That, by definition, we're just saying if I can't, if this value, there's nothing that's going to be consistent with y, and I have this dependency, then I know that that value cannot be what I'm going to assign to the x part. So I'm going to pop that off. So if I pop that off, I go ahead and delete it off and say, oh yes, revise is now true. So this antecedent becomes true here. And now I'm going to say the size of d is 0. That means if there's no values in the domain for x of I, then I'm in an inconsistent state. I might as well just stop because I can't solve the problem, right? Because I can't make an assignment there. Otherwise, I go ahead and I say, I'm going to look at all the other neighbors, ones that share arcs with x of I, and except for the one at x of j, because I've just already looked at it. I don't need to look at it again. And I'm going to add back into the queue, that link back into the queue, that arc, that constraint back into the queue. And the reason I'm going to do that is because now I've taken a value out of x of I. Right? I've taken a value out of x of I. So now I better go back and make sure I check those guys over there, that there's a consistent value from when they're the source, that there's some value in it that will hold true when the constraint, because now that value is no longer available. So notice that x of I is now on the second piece here And if you try to run revise on that, it's going to say, is there any variables for every domain variable here, is there always going to be something in x of I that will satisfy that constraint? And since we've taken a value out, we need to recheck it. And that's really the answer to this question. Right? We have to go back anytime you alter the domains. Okay. So that's a way of looking through it and enforcing this and reducing the possible domains for each of the variables. So what's the complexity of arc consistency? Well, in the worst case, you're going to have arcs from every node to every node, right? So you're going to have an n squared possibility. Each arc is from x, y can only be inserted on the agenda d times because you can only remove it d times, the number of values that can be assigned. Checking consistency of arc can be done in the order of d squared time. So the worst case is this still pretty nasty number. All right. So it's bad. And so what you're looking for is these heuristics to be on average to do much better. But in the worst case, CSPs are still bad, except for in particular cases. And if you can find these particular cases, and you can prove certain properties about the graph, there are tailored solutions that can be better. All right. So one of the properties that they talk about is the graph being k-consistent. A graph is k-consistent if for any set of k variables, you imagine you have a set of variables, and you take k, 5, 4, whatever number set of variables, and there's always a consistent value for the kth variable given any consistent partial assignment of the other k minus 1 variables. So if you have some assignment of those other ones, then you'll always be, if you have a consistent assignment of the k minus 1 set of variables, there will always be an assignment available for the kth variable. That's what it means to be k-consistent. To be strongly k-consistent is sort of this kind of, it's even holds a little stronger. It says if you're k-consistent, you're also k minus 1 consistent, which is you're also k minus 2 consistent, you're also k minus 3 consistent. So it holds true for as you all the way go down. So it's a little stronger statement of a property. Some of the things that you get from this is that if something is strongly k-consistent, you can imagine you actually don't have to backtrack, right? Because since you're going forward, and you always have an assignment that's guaranteed by this k-consistency, or this k-strong consistency, there's no reason for you to ever have to backtrack. As I said, these higher forms of consistency offer stronger forms of constraint propagation. They're kind of specialized algorithms that take advantage of these properties, and they can do much better than the generalized form. Okay. So some of the things with the intelligent backtracking, this is a way of trying to, again, to reduce the complexity of the search in its worst, which is going to be exponential. One is we've already talked about is this chronological backtracking. Always backtrack to the most recent assignment. If this assignment didn't work, you go back to the previous one. Not very efficient because sometimes you may know why you have a violation, and that may have happened much earlier in the tree. So one of the things people often do is they develop these things called conflict sets. And I'm not going to give you a formal definition of conflict set, but we'll talk a little bit about the properties of what you're looking for in a conflict set. But a conflict set basically says, these set of variables are going to be in conflict with each other. All right. I've discovered this when I looked it down. I tried to do an assignment, and I found a conflict. And now this is the set that is in a conflict. One of the things you can do is after you have that conflict set is to backtrack to the most recent variable assignment in the conflict set. So if I see the conflict and I say, oh, it was that variable that I'm conflicting with, I'm going to go all the way back to there in the search, jump to that, and I'm going to start the search again there, but with a different variable assignment. All right? That's a pretty simple modification of the backtracking search. Every branch pruned by backtracking is also pruned by forward checking. It's a sort of, you can jump back to that and you won't go to it again forward. The better definition of conflict set, as you might notice, if you have a really, really, really good definition of a conflict set, meaning that it's really accurate in terms of what the ultimate solution is, then where you jump to your search is obviously going to be, just like your variable ordering and your value ordering, is going to improve your search. It's not easy in general. You have to really take advantage of the structure of the domain to find good notions of what that conflict would be. All right. One of the things, like I can give you a small examples in scheduling, what they have is you often will see, for example, if you imagine yourself wanting to have, I'll just show you. Actually, if you have a resource, for example, and you have a timeline, and you have tasks that are on that timeline, and you're trying to put a new task down, for example, and you say, oh, I can put it in this slot, an empty slot here, or I might put it in this slot, an empty slot here. That might be some simple idea here. But if I have a task that's like, it's pretty long, has a wide allowance, it can be scheduled anywhere in between here and here, but it has a duration about that long, right? Then you're going to be looking and you're going to try to say, well, I'm in conflict. And maybe if I were looking at it, I might be in conflict with these two tasks. So these assignments would represent conflicts. And these might be part of this is one way of defining the conflict set. And you might say, oh, if I take these off, jump that out of the search, and then go ahead and put this one on and make that assignment here. And now I'm going to look for new assignments for these and see if I can get a better solution. Okay. All right, so we've talked about doing CSP sort of with this recursive search, or backtracking search. But another way to do it is just like we talked about before, is with local search. Remember, with local search, we start with a complete solution, and then we try to iterate over that complete solution by finding a neighbor, and then testing to see if that works out better. So again, we start just like that. We start in a state in some assignment of values to variables that may violate some constraints. So for example, the A queen problem, put the queens down on the columns. That's a state. They may be in violation. It's not a solution. That's a start state, right? And then we're going to do the successor state, which is basically say, all right, we're going to make a new state. And we're going to change that state that we started with by some way. And presumably, we're going to change it so that we will improve the state. Fewer conflicts, maybe. All right? And we're going to use this kind of heuristic repair method to reduce the number of conflicts. So what's an obvious one? What you would want to do is one heuristic is called this min conflicts heuristic. And that given a way of measuring the number of conflicts that the state is in, you then are going to try to move to a state that reduces that set of number of conflicts. This local search can actually solve the million queens problem in an average of 50 steps. In an average. Worst case is still going to be horrible. But in many, many states of the board, that does a very good guess. So what is, let's look at this min conflicts approach to it for doing local search on the CSP. Starts off with a CSP and then max steps, because remember local search, unless you it's kind of semi-decidable. It may stop if you find a solution, but it won't stop unless you put some kind of threshold on it, because we're just looking at neighbors. A constraint satisfaction and the max steps. Here we're going to have a current, which is a complete assignment, that initial state that we start with, a variable that you're going to change, and the value you're going to change that you're going to assign that variable to. So you just start off with an initial state here on this current state. And then you go from 1 to max number of steps that you're going to go. And then you're just going to randomly choose a conflicted variable. You're going to pick one of the variables that's in conflict. And you're just going to pick it, all right? And then you're going to take a value. And then you're going to take of that value, you're going to choose the value that minimizes the conflicts of that variable. You set that variable to that value. If the current is a solution for the CSP, then great, you're done. If you don't have a solution, go back, try it again. And you keep doing this till you do max number of steps or you find a solution. Pretty simple, right? So let's take a look at a really easy way to do this. This is a really simple A queen problem. And suppose, as I told you, we have variables for each of the columns. And the values are the rows that you're going to choose for each of those variables. So we start off the board with this board. That's our initial state. Just picked it and that's it. And we say, all right, we randomly pick a variable to change that's in conflict. This guy, this guy's obviously in conflict here. So we randomly pick it, and now we look at all the possible values in the domain for this guy and look at the conflicts for each of those values. So if you look here, here's 1, here's 1. Right? So that's 2, 1 up here, 1 here, right, and then 3 here, 1, 2, 3, and so on. So you can see how they calculate the number of conflicts for each one of those positions. As we move up here, we see that we have, these are the 2 value assignments that are the minimum ones, so we randomly pick one. So we go ahead and pick one, and we move it here. This becomes the new state of the board. Now we're iterating back through. We iterate back through, we randomly pick a variable that's in conflict, we pick this one. All right, so we see this, and we again figure out all the possible conflicts, and we say, oh, lo and behold, here's our minimum one. So then we choose this one. We have a conflict-free board at that point, and that's an assignment that solves the problem. Now, you're right. It's a little bit lucky to get it that quickly, of course, but for demonstration purposes, it's great. But the point is that you can do these very fast, very quick. All right. You don't want this computing this number. You don't want to be a very expensive operation. So you have to keep that in mind. But you can do this very quickly, very fast, and you can try lots of different number of states, and you hope that you converge to a solution very quickly. As I said, for the million queen problems, it in most cases will converge very quickly. So here's a small scheduling example, just to give you a sense of, again, something like, this is something you might do in the real world, where you're doing some kind of resource allocation to tasks. You have this process that consists of a set of tasks that are constrained in some partial order by temporal parentheses constraints. This has to get done before those 2 things get done, before that gets done, before that gets done. And each of those tasks has capabilities that's on it that it requires to get it done. I need somebody that can, screw the hole faster than anything else. So you have to have certain capabilities for those resources, and you're assigning those resources to those tasks at particular time points, or at least in an order. So each task can be a common set of resources. They may be multiple sets of resources that can satisfy the task. Some tasks may require more than one resource. The problem is to schedule a task in such a way as to limit the amount of delay caused by the lack of resource availability. So already now you can see this is not quite a constraint satisfaction problem, right? This becomes a constraint optimization problem because we're minimizing the amount of delay. If we're saying assign it such that you don't violate any deadlines of the tasks, then we're back in the constraint satisfaction problem territory. Okay. So you have variables, you have values, resource assignments. The general algorithm is you'll figure out some critical path analysis, basically to give you a ballpark of when those tasks can be done without violating constraints with other tasks. Choose a task to schedule using the variable ordering heuristic. You figure out, all right, now I have all these tasks and I have all these resource assignments I have to make. Which tasks should I start processing first? So that's my variable ordering selection. The value ordering is figuring out which of the possible reservations of all the resources do I assign to that task. You could figure out all the orderings with all the possible values, and it would be an exponential problem that would be gigantic and not practical. All right. Typically, what you see in most of these scheduling things is that you'll figure out sort of heuristic search for constraints type of scheduling. There are other types of schedulings which will work for optimal scheduling problems, but they're much more highly constrained. The idea here is that you then will go through and you will pick them, and depending on what you might pick, some simple heuristics might be like, I'm going to do the one that has the earliest deadline first. And that'd be an earliest one. I'll do the ones that start first, and I'll do them in that order. And but the truth of these kind of scheduling things is that there's no guarantee that they will result in the the metric that we had assigned, which is that we wanted to reduce the amount of delay caused by the lack of resource availability. They might give you an assignment, but it may not solve you this problem. So you keep trying to look for these things to see if you can find it. Typically, we won't do it in the real world. We won't do an exhaustive search because you don't have the time to do that. So, in general, there's different heuristics result in different schedules. Some of them might be better than others. None of them are optimal usually. Still cannot guarantee quality and schedule. It depends on the individual problem. Not all solutions are possible. What do you do? Well, one of the things is that if you find a solution, but like I'm violating the deadline, then I'm saying, nah, I'm going to try to do something maybe like that, or I pull back and I try another assignment to a variable, a backtrack, or I can try local, sort of like local search techniques. There's a technique called task swap, which in fact does that local search technique. Or the other thing is basically to you relax your problem to a certain extent. You're allowed a certain amount of relaxations, and that means that you accept a less than optimal solutions. Okay, so all of this was a introduction to constraint satisfaction problems. I didn't want to go into great depth to it. There's a huge amount of literature out there. It continues to work. Lots of people are devotees, almost, I would say, zealots of it, because they feel like almost any problem can be solved in this way. The biggest factor that they've had is that you have not seen widespread adaptations of this in real-world applications. You will see it in small example problems, but for very large problems where you'd like to see the benefits, where there are a lot of interdependencies, a lot of interconnections between lots of different spatial constraints, temporal constraints, all kinds of different loads and weights and physical capabilities. You won't see them as often. You do see them sometimes in design applications where you're trying to figure out like layouts, layouts for factory floors, layouts for chip design, all those kinds of things where you have lots of different constraints. Certain things can't be near other things due to the power consumption for heat or anything like that. And these things have worked pretty well for that, although again, the complexity of these problems increases very quickly and rapidly, and finding good heuristics that work in particular domains is still a challenge, and often you'll see papers just on those good heuristics. All right, so I gave you an example of the CSPs here now. Now I'm doing a little digression here, not really a digression, but I'm taking advantage of that. I'm actually pleased, given that Zico told me that we may be doing a different lecture. I was going to fill this spot in with something that's part of AI, but it's a little bit different. But it's not. I didn't want to go directly to planning because I didn't want to break up planning. So I was going to do a little bit talk about Blackboard systems. All right. Blackboard systems are. This is the kind of, now you can take your head out. We're not talking about an algorithm here. We're just talking about an architecture that is often used in software. Well, used more often in the past, but it's still used pretty often in software architecture. But now you'll think of different names for this. But before there weren't different names for this. So what Blackboard systems are is it's this notion of, think of this architecture that we're going to come up with an infrastructure. And in this infrastructure, we're going to come up with some way of trying to capture this activity where we brainstorm. And you have a bunch of experts out in the room, and everybody's trying to contribute to a solution to a problem, but no one knows the direct solution to that problem. So, as I said, these experts work as a team. They all go up and they write on the Blackboard, and then somebody will say, "Oh, I see what you're doing here. I'm going to work off of what you've worked off, and now I see what you're doing. I'm going to work off of what you've worked off of." All right. So they're all written on the Blackboard, and then the experts watch and contribute their expertise on the Blackboard where possible, trying to hone in and focus finally on a good solution for whatever problem you're working on. Before going into exactly what Blackboard systems are, I'll talk about some of the things that AI systems that use Blackboard. Hearsay 2, which was the famous Blackboard system, and was developed actually here at CMU with Lee Ehrman and Raj Reddy and Victor Lesser. And what it worked, again, was this idea of people doing speech understanding. At that time, speech understanding wasn't as developed as it was, but the main thing they came up with was this very intricate architecture that allowed a lot of flexibility. Some additional pieces that were done was HASP, which was come out of Stanford, which was interpretation of sonar signals. AGE, which was this generalized structure of HASP. Again, Boeing had something called OPM, which is this planner they had. And when we talk about planning, you'll see there's an element of search in the planning. But one of the things that happens is that instead of starting from initial state and going and working towards an end and being linear about the way you do things, you do something that's called opportunistic search, which is that you start sort of growing areas that you believe that are going to be possible. So you'll see some variables over here. So I'm going to grow this, and I'm going to grow this. And then the solutions, if they hit each other, you start to have a cohesive solution. And that's called opportunistic reasoning. So this was one of those. This was an opportunistic planner. This was a sort of a generalized form of that. And then finally, there's a framework that's out there that allows you to use lots of these pieces that were developed as part of the Blackboard systems. So some of the applications that were built in addition to that were this JEST, which is this was something that was really like a hierarchical rule-based system. We're not going to do rule-based systems in this class because they're sort of not used anymore. But you guys should probably be familiar with what they mean. And I'll give you just a very, very brief definition of what you'll sometimes hear them referred to as production systems also. So we'll talk just very briefly about that. HCVM was again, this notion of this framework for doing sort of this opportunistic reasoning in different ways to cut through some of the, one of the things with flexibility is that you often got inefficiencies, and this was trying to be more efficient. And again, same thing with this thing, very similar kinds of things here. DVMT was a system for doing tracking of vehicles going through space, and they'd have like ghost threads, and you're trying to figure out how to track based on their sonar signature, based on their radar signature, all kinds of things like that. And that system was developed using a Blackboard. This protein was the solution-born 3D protein structures from NMR data. Again, it was trying to grow the proteins and see them not knowing which way they would go. All these different things, pilots, associates, again, was a long line of DARPA-sponsored situational awareness programs. And the idea here was to have, again, make better advancement of situational awareness. So let's just go on here. So just some general areas you see it in. You see them in real-time systems, Blackboard systems. You see it in sensory interpretation, as we've seen sonar signatures, speech recognition, things like that. Design and layout, where you're trying to, again, do different constraints, but you're not sure how they hold together, so you're trying to keep multiple models in play. Process control, planning and scheduling. Often you see it, as I said, in real time, where you're closing the loop between execution and scheduling and having to replan when things go wrong. Computer vision, you have lots of different hypotheses about how things are being put together based on the data that you're getting from your sensors or from your visual sensors. And you try to make hypotheses about what you think objects you're seeing. And this is a way of formulating those hypotheses. Lots of different pieces. I won't go into great detail about each one. So what is a Blackboard system? It's a simple problem concept. Basically, you have a bunch of expertise. Think of these all as being different expertise. And they're all going to interact on some centralized Blackboard here. All right? And the idea is, how do you take their individual expertise and find some way to accrue them together into a greater solution? It's extremely subtle and open-ended in realization. It seems like a really simple idea, but one of the things that's key to this factor is that we have data on the board, and we usually have something else that's called control over here. And how these things interact is going to be governed by this control piece, rather than having what we normally have, which is this structured way of saying modular A is going to call APIs from modular B, which is going to call modular A, which has a more static but more understandable control. If you imagine these things can be reordered dynamically, but how they're going to contribute to a solution on the Blackboard, then you can imagine that's much more difficult to understand, but also gives you greater flexibility. All right. So as I promised you, I'm going to do a little contrast. Here's our one and only quick introduction to rule-based systems. A rule-based system essentially has this notion of you have a bunch of facts that are in memory, possibly, okay? And you have a goal that you want to get to. and you want you have a bunch of rules here that are in the form of if then else, or if then rules, I'm sorry. And in the if with the antecedent, you have some set of a pattern, and if that pattern holds, if Zach is 5'10 and he's 50 some years old, and that's true, then I can go ahead and assert the antecedent, which might say, something about Zach there. Okay, and you can put a new fact back into the working memory. And the thing that does the ability to assert new facts into memory is this inference engine. And it's either going to do something by backward chaining or forward chaining. All right? So that's typically what the rules are. One of the complaints about rule-based systems is that a lot of times you can have a state here where many, many, many rules might match up to it. And then what do? And you have something that's called, you have to do conflict resolution there. You have, which rule do you choose to assert first, basically, given that that may happen. And one of the things they had was something that they might do is say, well, I'm going to augment each rule with a priority, 5 here, 4 here, criticality value. And that was in a system that came out with some long ago, something called Mycin, which was for doing analysis of blood and pathologies. But anyhow, the point is that you'd put that 5, and you say, well, 5 goes before a 4. That's how we do resolution. But that was pretty simple, and there were many times you'd get into really hairy situations. So you had a uniform inference engine, but you had control and data tied together in the same rules, and it didn't take into account context at all. Lots of rules, fine-grained control, mostly working memory changes are significant. All right. So now let's take a look at the Blackboard. Wait a second. Right, Blackboard. So in Blackboards, you have this idea of this explicit control shell. This says basically that as you start posting things on the working memory here, and then you start matching up your knowledge sources or your rules of that extent against what's on the working memory, you don't just willy-nilly do it, or you don't have to do resolution. You have a more sophisticated notion of this control shell that sits outside of it and analyzes the context and the state. So let me go here a little bit more. The terminology that you have in Blackboards is that you have a Blackboard, which is where all the data lives. Typically, the Blackboard is an n-dimensional space, meaning that you can do retrievals on it based on queries that come from those n dimensions, any one of those dimensions you want, meaning that it's also a structured database which you store units on. You have knowledge sources which represent modules, and modules represent this notion of expertise of an expert. So these might be an algorithm, this might be any kind of specialty information. And then you have this control shell which determines which one of these knowledge sources is going to go next as you iterate through to apply to the data on the Blackboard. So here, let me just go through this example really quickly. This is the generic sort of architecture of a Blackboard architecture. Here's the Blackboard, here's the control shell, here's the knowledge sources. So the first thing that you would start, if a Blackboard system would start off with, it would likely start with one of two things. One, a system initialization event. That just says go, basically. Or it will start with something like an outside data feed coming in here. So this could be any kind of data that says something like, here's some new stimuli about a sonar signature, or new visual data, or here's a new state about the world. I'm executing a plan, and this guy just completed, this task just completed, or I have a new goal I need to solve. So any of those things can initiate the processing. When you post that on here, different kinds of events, depending on how you define your structure, can fire at that point. When those events fire, those events will then go into and match against preconditions on these knowledge sources. So if it's like, oh, I added a new data unit about a visual stimuli, some kind of for a vision problem, like, oh, I got a new picture that I just put in here, then it's going to look here and see if any of these knowledge sources are going to be triggered by that new data. When that new data comes in, any one that is triggered is added to the queue that exists here, or the agenda that exists here. And then you have all the ones that are possibly can go next. And that actually that goes right here on these pending KS activations. The control shell's job is to determine which one of these then gets to go next. Notice if you have more information coming here, as in a real-time system will have, that's also going to be adding things to here too, because you're going to keep adding pieces here. So you keep adding things here. It's going to add this. It's going to find it. It's going to have an executing KS. This executing KS will do the module part of the KS, which will then possibly change the Blackboard, which then in turn can trigger its own events, which can then again start this whole process again. All right. So event processing is nothing new, and you guys all do event processing kind of loop. But this idea is just using these events to make these kind of structures on the Blackboard that you can then combine different expertise as they're represented in here towards a better solution. The hard part is to determine how to combine disparate expertise into cohesive solutions. All right, so the character of a Blackboard system is this large-grained cooperating system knowledge source problem model. You can use a lot of different expertise and representations in these things, but it doesn't solve the problem of like when eventually you have to have these representations be able to interact, and you still have, you're still responsible. There's no panacea for that, right? KS interact anonymously using shared global database. That's the Blackboard. I said it serves as a way of sharing information across those experts and knowledge sources. It serves as a way of building up that information, and you can also put control information. It provides context, so the control shell can determine, oh, given that context, these guys should go better. But again, you have to recognize that context, and that's still a hard part of the problem. And the Blackboard serves as a trigger mechanism. You put things on the Blackboard, it causes events, that triggers other things to be done. As I was talking to you before about the opportunistic or island driving planning solution, opportunistic problem solving is directed by explicit control component, meaning that if you have KSs all sitting in that pending KS queue, but you're working on some hypothesis that's on the Blackboard, the control shell can say, oh, that's more important, so I'm going to bring up the guy that's pending here because I'm working on that hypothesis, and I can change my focus to work on that guy. Or if that hypothesis seems like it's losing in its weight and it's not being very credible, I can change focus through my control shell by looking at what's happening on the Blackboard. So on these kind of problems that are being solved in Blackboards, typically there's like no consensus, but there's often some notion of working towards a solution. It's usually done incrementally. You're working up, if you have hypotheses about what you think you see in your vision data, and you start working them up, and you're working them up, and suddenly you say, all right, this is the one that has the most credible solution. But I'm trying to, meanwhile, I might be keeping viable other options available until I find the ones that are most compelling. You might want to structure the Blackboard. Certain pieces, you want to look at, you have higher level and lower level, you have abstractions. Typically, what you might do is say, here's some lower level data. I'm going to grow it bottom up. This is suggestive of some hypothesis up here. This is a higher level one. And because the more I find about this higher level one, the more I can find compelling about lower ones participating in that. And so you can have sort of this top-down, bottom-up kind of driving of trying to solve solutions for certain problems. That's what I mean by the island driving. Again, the competing hypothesis, as we talked about with the vision before, this is really key. If you can keep multiple hypotheses that you're building on and keep them in play at the same time, kind of like search in that sense, but a little bit different way of doing it. You can, you can keep allowing each one of them to be sort of magnets of data and see if they're being supported and see which one works better. Blackboard's used for control information. You can see what happens. You can follow it through. Reflexive control, when systems have to interact with each other, the modules have to interact, they can self-referent through the Blackboard. I think, that gives you lots of different notions. All this slide is talking about here is talking about in our traditional programming systems, non-event-based ones, we have these sort of very API-oriented modules that interact with each other through static interface controls. Blackboard is a little bit different. All these Blackboards, all the modules, instead of pointing to each other, they point to the state on the Blackboard. And the Blackboard, wherever the state of the Blackboard determines the interactions among the modules. Okay, so you can see it's enough rope to hang yourself, but it's also it is also a way of being much more flexible and being dynamic, especially as context changes. So let me just go into, let me get to, no, we don't get it. No, these are, what these are talking about is just sort of some of the advantages which you can imagine, which would be there's modularity, the fact that different people can work on different knowledge sources with their expertise and then only get together and join them together. You can put wrappers around legacy algorithms so that you can just go ahead and interact with other algorithms very quickly. So it helps when you're designing collaborative software applications using some existing algorithms or legacy systems plus new algorithms that you're adding, and they all interact with the data representations that you put on the Blackboard. Okay. Some of the development strategies when you're doing a Blackboard is you have to determine the structure of the Blackboard, how you want the different databases to look, the dimensions that you might be doing retrievals on. You have to figure out the language that you want to use. There are languages for the independent reasoners, the knowledge sources, and then there's probably a language that's going to be above that, which is the language that's used across the different knowledge sources. So this is actually for every programming problem, it's always a very difficult issue. Things that you can do, you can use things that already exist, certain kinds of ones. Problems. One of the problems with doing some of the legacy stuff is that a lot of legacy stuff is expecting the entire problem. So you have to often import that whole state of the world into that problem, solve it in there, and import back the solution. Again, there's prototyping information, lots of different ways to do this. Adding control is a really big piece. As I've been talking a lot, I've been saying that you have these control shells which are independent of the data that you're actually using, of the knowledge sources that you're using. But you have to be able to recognize certain things. On the Blackboard, if you're going to do context-specific triggering, you have to recognize certain states that arise. Another way that you do it is this more general way, is that each knowledge source says, I'm so important. I'm a 5, I'm a 4, I'm a 3. And then the Blackboard itself can determine which one's more important, either by classifying by the tops of the knowledge sources or just doing a flat rating, or lots of different ways to do it. But you can change that. Remember, wherever you implement, you can then go ahead and change that at a later point as you explore the interactions between the knowledge sources, where instead of having it tied directly into the rules, where you'd have to go through and change that, or into the static structures of the API, here you can kind of go ahead, run it, explore it, and then go ahead and change the control on the outside and watch those interactions be a little bit different. Okay, let me just do this really quickly and then we'll end up. I just want to go through the hearsay 2 and to give you an example, more concrete example of how Blackboard might be applied. This was the original one. This was for the speech recognition. Pretty modest goals given today's technology, but back then these were pretty stellar. 1,000-word vocabulary, 90% functionality, 1/10 real time with a single processor, and it was a very slow processor at that, and 15 knowledge sources. Okay, so one of the things that Hearsay 2 was to reduce search commentaries using abstraction. So when it would see a little bit of information, it would posit a hypothesis about what it thought. And as it got more information, it would increase the credibility of that hypothesis of what it saw, or it would reduce it. As something became more credible, as new data came in, it would be sort of like a gravity well, and it would say, oh yeah, this actually works better, like that. So you could sort of grow, if I said, from the bottom up and top down. Opportunistic application of diverse knowledge. We use different levels of knowledge that it was applied to at the level of morphemes and abstractions and words and sentences, all the way down to the independent signals that come in from the speech recognition. There's a lot of unreliability in the sensor data, and so you needed to sort of have a model that would deal with the uncertainty. And so this thing, by having multiple hypotheses that it was growing at the same time, it did a very good job of sort of weaning out the hypotheses that weren't likely to come to fruition. There wasn't a known way of handling this problem, so they initially came up with a lot of different knowledge sources and different ways of growing that information, and I'll show you the state in a second. And then what they would do is they actually tried different control strategies to see which ones would perform better. Because they didn't really know. They knew lots of ways of breaking down the problem into different components, different abstractions, but they didn't know how to combine them. And so they tried lots of different things here. As I said, then lots of people worked on it, and it kind of went through this, try it, experiment, see what happened, make a hypothesis, change the control structure, change some of the knowledge sources, try it again. And they were able to do that very rapidly because of this Blackboard architecture. Okay. They wanted to have parallelism. They did do that in Hearsay 3, but they didn't do it in Hearsay 2. So here's an example of sort of the various levels of abstraction you might imagine. You imagine as input comes in over time, you're trying to grow these things in terms of a parameter come in, a segment, they have a syllable, you might find words, word sequences, phrases, so you have this whole thing and they're trying to recognize what the phrase is. And what they would do is they take data and depending on which one, they would kind of push new hypotheses about each of these different levels. But it would start off bottom down, but then they would rapidly come up and make higher level hypotheses here. And these higher level hypotheses would in turn help to identify new information that came in here. And if they couldn't explain this new information, they'd again pose another hypothesis. And they would keep multiple hypotheses in play until they figure out which one was best supported by the data that came in. Yeah, so I was just about to go to knowledge sources in a second. There you go, okay. So here are some of the knowledge sources. So if you look back here, you have the segs, and you have all these things that you're building. Seg digitalized the signal. POM synthesized the syllable class hypothesis. Again, different levels of abstraction here. Synthesized the word hypothesis, the sequences here. So different knowledge sources were responsible for different levels of that abstraction. Parse synthesized the phrase. Predict predicts all the possible words before or after a phrase. Again, just to give you a context of it. I'll give you a sense of that. Verify checks the consistency between the segments and paired words. And concat concretes a phrase from verified phrase predictions. Well, now we're going to get to that. So they are working in sequence, but they're working based on the control shell. And they tried different control shells, which would choose the order in which things could apply, given a certain context. These are just some more of those KSs. So here, I'll just go to a real example. Here's the stimulus unit that comes in. This is the low-level information. You might have this input context, previous things that have come out, expectations about the input. And you have different information that's already been seen. And you might have already one existing hypothesis in your reasoning. And you look at this and you say, wow, if this data that I've got, this and this and this supports this hypothesis. So I'm going to keep evaluating the credibility of that hypothesis based on its support. But I might want to make a new hypothesis because it's not enough, and I see this, and this support this new hypothesis. So that's what these interacting KSs will posit new ones of these things, and then they become sort of supported hypotheses that are kept in view. And if they ever reached a point where they were not very highly credible, they would be dropped off. Just real quickly, the way the KSs work is in Hearsay 2 is they had this precondition procedure and an action procedure. The precondition said, oh, given a state that's occurred, I'm active, I'm ready to go, I'm pending, waiting to be applied, and this is the action that would be applied, like make the phrase or make the word, depending on what the KS was. Here's the scheduling criteria to answer your question about how ultimately they did it. But like I said, they tried many different scheduling criteria. And they did a lot of experiments, and they found things that would work. So at the end there, they attempted a kind of linear combination of scheduling criteria, the quality of the KS input data, how good it thought it was, the importance of it, given the existing hypotheses, different levels of hypotheses, the estimated quality of the KS output data, how strong did it support something, the output, estimated quality of the KS knowledge, the KS itself, how expert was it, basically. The performance, did it take a long time to run? It was a short time to run. Estimated global benefit of the KS output. So they had all these kind of heuristics and values for guessing this. They would combine them all together with some manual learning, and this failed. So the scheduling needed to be context sensitive. So they thought, oh, we'll just come up with some ordering. All right, we'll come up with some ordering, and we'll just apply those KSs based on this utility value. Turned out that they really needed to understand more about what was out on the Blackboard, and they had to do more sophisticated control. When they did that, they got much better results. They were able to say, oh, I have these kind of hypotheses, and these things are present. That's when I should do this one. So the main contributions for Hearsay 2 was, it was the original Blackboard system. It was a cooperating KS problem-solving model. Lots of different KSs applied, but none of them statically linked to each other. Had a competing hypothesis representation, lots of different hypotheses with different methods we throw away as they lost credibility, increase some new ones when they couldn't, the existing ones couldn't explain the data. The precondition action KS model, the identification of important scheduling criteria, like I said, that linear accumulation of all those values that they thought would be a great way to order. I mean, how many of you guys have ever made a program, try to assign values and say, oh, I'll just try it this way, the first way off. And it performs really poorly. And then you're like, oh, I got to do something a little bit more intelligent about this. And this allowed them to do that very quickly because the control was separated from the data. So you could really change, oh, okay, we'll try it in a different way here. And the development of numerous programming tricks. I'm not sure this was a contribution, but certainly these tricks have been used since then on Blackboard architectures. It was hard to debug, and it was hard to always recognize what was going on. That's exactly what you see often in event-based programming. So let me not go too far more with this. I didn't want to divulge too much into this. The one thing I wanted to say is that we continue in our lab to use Blackboard architectures. We've used it, one of the major applications we used it for was something called coordinators. It was C-Matrix was our system. This was a natural disaster tool for teams going out and having to explore and discover broken utilities and casualties and having to rescue them in a distributed way. This is a real-time system where data came in at a real time, and then they had to do planning and explanations on the fly. And what you had to do is get what was called sort of an anytime behavior, which means that you only had so much time to react, and then you had to do something. And so this allowed for us to have multiple hypotheses that we kept in play, and then incrementally try to increase them as we got new data, and go with different solutions based on those hypotheses that were being used. We had multiple Blackboards in this case. Each node, or which were tablets basically, that each person carried out into the field, ran its own Blackboard, and then communicated with the other Blackboards, sharing information that it thought was salient, such as boundary cases and things. And action saying, I'm going to go pick up this guy, you shouldn't go pick up that guy. Right? Don't go pick up that casualty. So this was a very useful model for that. It's also been a useful model in a system that was used for sort of this generic scheduling system that allowed lots of different ways of handling different scheduling structured problems. And there's certain ways that you could sort of optimize and optimally handle small problems using OR techniques, for example, and then combine them together in these general solutions through constraints. And so it was a way of applying that. That was called Ozone and Opus. Those were the types of models for doing that. So what I wanted to get at was just that the Blackboard architecture is something that's really flexible. It's not many things you're going to be exposed to very often. So I took advantage of this little break in between planning and CSP to give you a touch of that so that you can, if you see in the future, something that might apply to what you are going to do. All right, thanks.